Hi, and welcome again to our class on electrical systems in agricultural and biosystems engineering. This is lecture number 5. We are in the topic of conventional sources of electricity. Particularly, we are in on the topic of generation of power. But before we proceed with the renewable ones, we talk about the conventional sources of power. Now, let's proceed with the most conventional. Okay, and well, we're going to talk about the overall process of this power generation. We have here a schematic. Okay, the schematic or it's a diagram for most okay for most power generation plants involving the conventional sources of energy, such as petroleum, natural gas, oil, coal, and even geothermal. And this same diagram is usable for biomass and other combustion fuels, okay, like biofuels. Because particularly, it's the burning of those fuels, okay, carbon-based fuels that uh, operate this power plant. So we have the operation starting with the fuel or the energy source burning. Okay, so we burn the fuel, and the heat of combustion of the fuel boils a fluid, in most cases water, and it's turned into gaseous phase. Okay, for natural gas, petroleum, and coal, the fuel is burned according to um, specific combustion conditions, so that the uh, the fluid is turned into gas. For geothermal, water or brine, whichever is more appropriate, depending on the cycle being used, okay, the cycle or the operation. So later is going to be discussed in detail. Now in 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 geothermal, water or brine, okay, or brine is injected into a geothermal well, where the heat of or the volcanic heat, the bottom, it heats up the water or brine so that it evaporates. Same to the concept of the boiler in here. Now, as the water or the water is turned into gas, okay, the vapor, okay, the gas or the vapor, the gaseous vapor, is directed towards a turbine. Okay, the turbine, well, it rotates, and the turbine would depend. Okay, it varies according to the cycle being used. Okay, because there are specific gas turbines fit for the Brayton cycle. Again, the Brayton cycle is uh, the Brayton cycle is the uh, power cycle, okay, used in for this specific, okay, for uh, petroleum, okay, in coal. Now, the Brayton cycle, it operates similar to the heat engine cycle in thermodynamics. So it follows the laws of thermodynamics. And that's what I was referring to with the proper combustion conditions. Okay. Now, the geothermal power plant, it operates via the uh, dry steam cycle, flash steam cycle, and the binary cycle. Okay, so either whichever of the three is appropriate. There are also options nowadays to combine the power sources. So there are combined cycle power plants. We will not be going through all of this as technologies are varied and but they're upgrading these days, or the developments in the field is very much fast paced. Our focus is on the electricity generation using this the very key component. If you could see, the very key component in our power plant is the alternator. Okay, I will circle it. Now, the alternator in this diagram, it sits besides the turbine. And the turbine, again, it's rotating. Okay. Once the turbine rotates, it's coupled to the alternator, and the alternator rotates, and this is where the electricity is produced. Okay. So there is a shaft rotating, and that's now producing the electricity that is supplied to the grid. Okay. But okay, let's not forget about the vapor. If you can see, as the vapor goes to the turbine, the steam, okay, the vapor or spent steam, it goes back again where it condenses and cools back into liquid via the condenser. Again, if it's water, it goes, it becomes liquid again. And once it's done, okay, it goes back to the boiler to complete the cycle and being used and to be used again for conversion into gas or steam or vapor. Now we focus on what happens on the alternator, but before that, okay, let's just have the operational concept of AC generators, and this follows the this is in figure 2, okay, but we have the concept of the electromagnetic induction as shown in figure 3. This was first discovered by the self-learned Michael Faraday, but later explained by the British James Clerk Maxwell. Well, they're both British anyway. So in figure 3, we have the loop, okay, following the concept of electromagnetic induction, okay. We have a loop, okay, instead of just one wire, we have a loop of wire, and it is in between two opposite poles, okay. And it's just rotating, okay. This is rotating while being driven by the turbine, okay, or whatever mechanical force. So in here we have the turbine. So the loop is going to rotate, okay. Now there are sliding contacts via slip rings, okay. Here are the slip rings and conductive brushes at the ends of the loop, okay. And this completes the loop, okay, for the external load. This is, for example, this is the grid, okay. This is the grid, okay. You can say that this is the grid, okay. This is the grid, for example, okay. Okay. The loop, okay, as it rotates, okay, it experiences what? Experiences a magnetic field emanating from the polar ends of the magnets from north to south. This induces a current in the loop or circuit, and since there's an alternating direction, okay, of the magnetic field, because there's a constant magnetic field, but this, with respect to the wires, they are changing in direction. Now this induces an alternating current, okay, across the loop. Now let's proceed with what happens, or what looks like when we measure now the voltage across this loop. Okay, so we see, okay, in figure 4, the voltage induced by the rotation of the loop across the, or between a two poles of magnets, the across the magnetic field of the magnets. Okay, we see is a similar sinusoidal pattern consistent with alternating current. This is now the most important portion. Okay, and we take note that the orientation of the loop and its relation about magnetic field is causing this sinusoidal pattern or wave of induced voltage. The shifting poles is designated by the darker portion. Okay, when we have something over here, we have the north. Okay, going to the south. So as it goes to the south, okay, the other portion is now accepting the different direction. Okay, the way, or the flux of magnetic waves from the north. Okay, just for that. Now, all right, so we now have the here, okay, we have now in figure 5 the schematic diagram of operation of a DC generator. Okay, in place of the slip rings and the brushes are commutators. Okay, thus, okay, we have the load experiencing voltage from one direction, okay, as can be depicted in the sinusoidal chart. Okay, in place of the negative portion of the AC is of the AC generator is an opposite positive chart. Okay. Now, figure 7 is a representation of a basic synchronous, the basic synchronous alternator. And this is the common alternator used in most power plants around the world. Okay, the only difference of an alternator to a generator is that the magnetic field rotates about the stationary poles, which are in place of the rotating loop. Okay, the loop. Okay, the reason, okay, why there's a or the reason for this change or difference is that for very big alternators, okay, it would be very heavy. Okay, if unlike the poles are fixed. Okay, so contact of the or brushing is also causing a lot of wear and tear in the metals, and that would require a lot of maintenance. Now, in figure 7, we see only 2 poles, and that is for single phase. Okay, later we'll detail on that. That case, okay, we have the usual wave-like or the sinusoidal pattern as we have seen in or as we have already identified in AC. But there are also polyphase systems as shown in figure 8, and in a polyphase system, in here we have a three-phase setup, so that well, in the case of a three-phase alternator, we have the overlapping of those sinusoidal waves. Okay, and in effect, this actually causes a more efficient or results a more efficient system. Okay, because there is less loss of energy. from what? From the reactive power, okay? And thus we have more mechanical output, okay, converted to electrical power. Now, to compute for the frequency of the electrical system, okay, we use equation 1 as shown, and this is Pn over 120. The quantity Pn over 120, where we have the parameters, okay, P is the number of poles, and N is our speed in RPM, resulting to our frequency of F in the units Hertz. This is again for the sinusoidal voltage, okay, produced by any phase, okay, for however many phases there are in an AC generator or alternator. So in the next discussion, okay, in the next lecture, we try to solve the electricity or the electrical power produced in a conventional power plant. See you next time.